So last night we saw that every two-dimensional planar object, okay, an object in a plane, like a triangle or a semicircle or a diamond or a rectangle or whatever, if it was moved through that plane across the x-axis, it would create three-dimensional space. So today we're going to see how a two-dimensional function, just a curve, as it's moved rotationally through three-dimensional space, it will create volume as well. So it's another way to create volume. You can create volume by sliding something, but you can also create volume by rotating. So that's what we're going to do, the rotation around a fixed axis. Okay, so here's the rule. If f of x is always bigger or equal to g of x, okay, so if you have a function, and if you're drawing whatever function it is, if it's always higher than the other one, on a closed interval from a to b, and then the area between f and g is rotated around a fixed axis, then ... Okay, I'm going to pause the video a second. Okay, then the volume formed will be V equals the integral over the interval from a to b of pi times, and we're going around something, so this has got to be pi r squared somehow. Okay, so it's going to be pi times something squared. So it'll be the top equation minus what I'm going to call alpha. Alpha is the thing you're rotating it around. Maybe you're rotating around the x-axis. Maybe you're rotating around the y-axis. Maybe you're rotating it around a different fixed line in space, but it's going to be the axis of rotation. That's your radius, so that quantity has to be squared. Notice I've double parentheses that there. I don't know if that's a word, put double parentheses around that. Minus, now I've got to take away the space that was maybe on the interior. So that will be g of x minus that same axis of rotation, and that is squared. And that is a whole quantity. So the pi is applied to both of those. And then you're going to have your differential on the end. It'll either be dx or it will be dy, depending on if your axis of rotation is vertical or horizontal. So if your axis of rotation is horizontal, like the x-axis, you would have dx. If your axis was vertical, like the y-axis, you would have dy. Okay, so let's actually do it. I think if yeah. Right, if we're rotating it. If you're rotating it this way around the axis and the axis is fixed in a horizontal position, then it's going to be dx. And if we're rotating it this way, then it's going to be dy. Okay? I showed you this last year too. So it's as if you could stick your axis of rotation through the paper towels. Okay, my axis of rotation came through here, and at the other side, that's a horizontal axis of rotation. Okay, as opposed to this way, your axis is going to be going up through the middle, coming out that way. That's a vertical axis of rotation. Okay, the value of the volume is going to be the same either way, but how you compute it will be either dx or dy. Okay. All right. So let's do a sample. Let's create a two-dimensional planar object, and then let's rotate it. So let's say that f of x is cos x plus 2, and g of x is always beneath it, and it's 1. And we're going to be focused on the interval from -2 to 2, and we're going to go around the equation, the line y equals -1. Okay, we got to picture this. So cosine of x plus 2. Okay, so 1, 2, 3. If I take cosine of x and I shift it up 2, the graph will look like this. Okay, right? That's the graph of cosine. And so that's f of x. G of x is the line 1, which is just a horizontal line. And we're looking at the area bounded between those from the interval -2 to +2. So I'm going to use my eraser and I'm going to get rid of the rest of the cosine graph that I don't really need. Okay, I'm going to spin that through space around the line y equals -1. Now y equals -1 is down here. It's an imaginary axis which needs to essentially go through the center of the thing as I rotate it around. So when I rotate this around and keeping that green line, that axis line in the center, it's basically going to look like a reflection. So I'm going to have this down here, but it's coming around all of that. Ooh, don't like that. Okay, so this is rotating all the way around. Now can you, I'm not the greatest artist in the world. I'm really trying my best. Okay. To me, I think this looks like a bead. Do you guys know what a bead is? My international students know what a bead is? Something that goes on a necklace, has a hole in the middle, like a piece of jewelry. Okay. Can you tell that it has a hole in the center? Okay. And the outside is sort of curved, but it's got a hole in the middle. And you put string through it and you put it on a piece of string. Okay, so it's like a bead. All right, let's find the volume of that. Okay, Tron, can you picture that okay? Am I drawing not totally horrible? Okay, so we're going to set up our volume equation. So our volume is going to just simply be the bounds from -2 to 2 of pi. Okay, I take the higher of the two functions, which is forming the outer edge, and that was the cosine of x plus 2. And I have to subtract the axis of rotation, which is -1, so that'll be a +1. That quantity will be squared. In order to make a hollow center, I have to subtract away from it. It's like cutting it out. The g function, which is 1, minus the axis of rotation, which is also -1, so that would be 1, and that would be squared as well. Those are both radii. One is forming the outer edge radius, one is forming the inner edge radius, and then that whole thing is going to be a dx because my axis of rotation is horizontal. And after that, that's the hardest part, is setting it up. After that, it's just computing the antiderivative and plugging your values in. Okay, so at that point, we would have -2 to 2 of pi times cosine of x plus 3. That quantity would be squared, minus 2, and that quantity would be squared. And so we're then we're looking at cosine of x plus 3 squared is cosine squared of x plus a 6 cosine of x plus 9 minus 4. So you could simplify that to be pi on the outside. And we would have cosine squared of x plus 6 cosine of x plus 5 dx. In order to finish integrating that, you would need a trig substitution, because cosine squared doesn't integrate without a trig substitution. The rest of them would be fine, but I would need a trig substitution here, and the trig substitution is the half angle substitution. So we would have 1/2 plus 1/2 cos 2x. So that's the identity for cosine squared. And then plus 6 cos x and plus 5. And then from there you're on the home stretch. And you can just integrate each piece, because each piece has a perfect antiderivative, and then you plug in, I wrote my bounds wrong, then you plug in your bounds from -2 to 2. I'm not going to keep going because that's not the point of today's lesson, but from here you're just going to do an antiderivative of each part. How do you feel about that? I mean, the setup of it. Setup is okay? Okay, well, let's try another one. Okay, so let's try y equals the parabola x minus 2 squared. And then let's try the vertical line x equals 1. And we're going to try around the vertical line x equals 4. All right, so let's take a look at what that looks like. All right, the parabola x minus 2 squared is rotated or shifted 2 to the right. So this parabola would come like this. The vertical line, x equals 1, is just right here. And so the area that we're looking at is the area bounded between those two and the x-axis. I should have specified that. Okay, there's our little area. So I'm going to erase the rest of the parabola because I don't really need it. Okay. We're going to rotate that around the stationary line, x equals 4. So let's put that, there's 3, there's 4. So the vertical line would come through here. So if I rotate that around that vertical line, when I draw it, I usually make a reflection first. And so my reflection would look like this over here. And then I try and picture what that would be like. And so you have this outer edge, but you have a bowl-shaped thing in the kind of carved out of the middle. There we go. But there is definitely this bowl-shaped thing in the middle. The outer edge is solid, but the inside has that dome, inverted dome. Okay, all we got to do is follow the format for determining the volume of that shape. It's less about being a good artist and more about just being able to set up the equation. So we're going to have pi times. Okay, which function is forming the outer edge as it rotates around? The 1. And so that would be 1 minus the 4 as your axis of rotation, and that will be squared. Okay, then minus what's forming the interior. Now you got to be careful here. has to be in terms of y. This is going to be a dy equation, and so my parabola needs to be converted into a dy equation. Yeah, so you come back here and you're like, all right, so I'm going to have plus or minus the square root of y equals x plus 2, x minus 2. And so x is 2 plus or minus the square root of y. Okay, and which one do we want? Okay, do we want the plus or do we want the minus? All right, what do you think? Okay, now you're going to go on which side of the parabola is like this, right? Where, okay, and so which of those two sides? This would be considered the minus side of it, the left side of the parabola, because this parabola was, let me see if I can draw it on there. The parabola was originally right here. Okay, and we want the left side of that. So 2 minus. And so we're going to be using 2 minus rad y minus the axis of rotation, which was 4. And then let's do our bounds. But remember, the bounds have to be y bounds. So how tall is this figure from 0 to 1? Okay, because those have to be on the y. It's not 1 to 2 on the x-axis. It's 0 to 1. That is truly the hardest part, is getting that set up. Once you have that set up, okay, well, I could pull pi out to the front. My bounds are 0 to 1. I've got 1 minus, that'll be negative 3 quantity squared, minus, that'll be negative 2 minus y, that quantity is squared, and the whole thing is dy. So it just becomes a matter then of cleaning up the arithmetic. So we're going to have 9 minus 4 plus 4 rad y plus y dy. And then we distribute the negative and we combine the 9. So we'll have pi is 0 to 1. We'll have 5 minus 4 rad y minus y dy. And then you can do the antiderivative of each piece once you're that far. If your homework, if the book lets you use your calculator, by all means, go ahead and do an FNInt on this, okay? Don't bother trying to do it by hand if you're allowed to use your calculator. So on the AP exam, you guys have experience with this, Trung doesn't. On the AP exam, if it's calculator part, you even could just stop here. Sorry. Okay? All you have to do is write the integral. Because sometimes you might lose points, because what if you wrote the integral, but then you did some math wrong down after that? Okay, just like stop and write your integral, and then type that into FNInt and let the FNInt calculator do it for you. If it's calculator part of the AP exam, it's calculator part of the homework, calculator part of the test. All you have to do is write a legitimate integral. You can leave it in an unsimplified form and use your calculator to do the rest of it. The only time you'd have to simplify if you didn't have your calculator and you were supposed to do the whole thing by hand. So I'm going to try and save you time on your homework tonight. Feel free to use your calculator if it's calculator active. All right?